Our first speaker is Wenlong Mou, and he's a PhD student here in Berkeley, advised by Martin Wainwright and Peter Bartlett.
Yeah.
Works on many aspects of machine learning and sampling and optimization. And today's talk is about higher order Langevin diffusion.
Thanks, Santosh, for the introduction. So I'm Wenlong. Today, I'm very happy to present my work on high-order Langevin diffusion using an accelerated MCMC algorithm. This is a joint work with Ian Ma, who's supposed to be sitting in this room, but she didn't show up now. And my advisors, Martin Wainwright, Peter Bartlett, and Mike Jordan. So let's start. Let me first give some preliminary results. I guess those discussion would be like familiar to most of the people in this room, but it is still good to go from the very easy problem, easy algorithm to see where the difficulty lies in, and then slightly move to our main theme of discussion, which is our high order Langevin algorithm. So we consider, as all the most of other talks for today and this week, we consider log concave sampling problem. You have a potential function f with beta smooth and mu strongly convex. And of course, there are a lot of applications for sampling. That's why we are sitting here. There are Bayesian inference and sequential deflation making. And for those problems, the dimension of the space that you are trying to sample from is usually very, very high. So that's why we are so interested in finding algorithms with lower and lower dimension dependency. And this talk is also about getting better and better dimension dependency for sampling algorithms. And in particular, for reasonable class of problems, we get the best known dimension dependency without too many additional assumptions. So here's what everyone knows. This is just a Langevin diffusion. You just have this stochastic differential equation, and it has under mild regularity conditions. It asymptotically converges to the stationary measure, and you can use standard coupling method. Under strong convexity, you can use standard coupling method to show its quantitative convergence in the continuous time. Everything is nice. If you try to discretize that, know that actually I wrote a relatively non-standard form of discretization of the forward Euler method. But essentially, what you are doing is within a small time interval, instead of running the original diffusion process, you run a Brownian motion with constant drift. And the drift term is coming from the initial point of this interval. And this is a very natural algorithmic idea, and this is analogous to gradient descent in optimization. And this algorithm has been intensively analyzed under different settings. And so where does the discretization error for this algorithm mainly come from? So basically, what you do is you replace this theta t by theta k eta by the point at the initial state, and the difference between these two guys is of order root eta d, because you drive it by a d-dimensional Brownian motion, and its fluctuation is of order root eta. So this leads to of order root eta d discretization error. If you don't assume any other assumption, this is very classical work. If you further assume the hashing of f with Lipschitz in terms of operator norm, actually you can get improved result. And the nice aspect of this result is that this result doesn't actually require the convexity of the potential function f. So, of course, one may ask, can we do better? And there are existing works that improve dimension dependency, which is the underdamped Langevin diffusion. And the reason why the underdamped Langevin diffusion is better is intuitively it moves the Brownian motion part to the part that does not directly involve taking the gradient. So basically, the Brownian motion part appears in R, And here you basically when you want to take discretization, you want to take gradient ff at a discrete point, and you want the curve for theta. You want basically the path for this like a different stochastic differential equation. You want the theta part of this path to be not that non-smooth. Like we know that Brownian motion, roughly speaking, is like a half order Hölder. But if you integrate it once, you get like basically 3/2 smoothness. And this helps a lot, actually. This gives like root D mixing time for underdamped Langevin algorithm. And I just want to mention that the proof for the like convergence rate for this continuous time diffusion is also not that hard. You basically take a synchronous coupling and you take this Lyapunov function, and you can show that this Lyapunov function is decaying at an exponential rate. And the reason why I want to talk about this is because the idea of a construction for the third order Langevin diffusion is also like following a similar path. And you will see that using like integration oracle and like third order, more complicated Langevin diffusion, how this thing can further improve the dimension dependency. So here's the discretized version of the underdamped Langevin diffusion. As we see, what people actually do is simply by replacing the theta t with theta k eta hat, which is the point, again, the point at the initial state of this. And this differential equation is solvable with the explicit solution. It's just the OU process jointly in theta and r. If you give me an initial state and the gradient of f, I can directly write down the like one-step transition kernel. It's just a Gaussian one. And the reason why this guy gives like root D by epsilon mixing time is also it follows a very intuitive analysis. So the theta process, as I just said, it is much more smooth than the theta process in the like overdamped Langevin diffusion, but you still pay for some dimension factor here. In particular, you run within like a eta time interval, and this RT process is like it's just a generic vector in this space, and you can think of it as something like with distribution like Gaussian-like or sub-Gaussian in every direction. And this thing has like norm bounded by of order root D. And then you substitute into this process, and you'll show that the one step, you can see that the one step discretization error for this R process is of order eta squared times root D. And that means the discretization error for the R process itself is eta times root D. Sorry, there's a typo. This should be theta t hat minus theta t. And in the end, you get the discretization error for the entire process is of order eta times root D. This just coming, this eta times root D no longer comes from the very wild oscillation of the Brownian motion. It comes from very well controlled process. It's just you have a like a generic like Gaussian like vector in this R-dimensional space, in this D-dimensional space, and you try to integrate that, and you use the starting initial point to approximate this integral, and this naturally leads to eta times root D discretization error if you take eta, if you take your step size to be eta. There's nothing like much more we can do here. And after this work, there are also some follow-up works on like several different directions. So as I just said, for Langevin diffusion, for the unadjusted Langevin diffusion, basically you have to pay for linear in dimension, and there are some like improvement in terms of epsilon dependency, but the best known dependency on dimension is linear, unless you assume some like more unrealistic like assumption that could further hide the dimension dependency. For underdamped Langevin algorithm under the same set of assumption, you can get like root D dimension dependency, and there's a further improvement by Ruoqi, who is also sitting in this room, which gives you like d to the 1/3. This is based on a very smart idea of taking a random midpoint instead of just the initial point or just the midpoint of the integral. But it's just hard to further improve this dimension dependency along this direction. And there's Hamiltonian Monte Carlo, which gives you results that are in the form similar form as the underdamped Langevin diffusion, which is reasonable. And also there's work by Santosh and co-authors, which impose like stronger assumptions on the. Basically, they consider like a generalized linear model where each data is the data are somehow mutually incoherent. By incoherent, basically it means that the inner product between two data points are bounded by a constant. So basically, the data are like pointing to very different directions. So if you have two data points that are very close, then this assumption gets break down. So as you see, this works, although like gets improvement in certain regimes, it is this assumption is generally very strong. And this our work further improve the dimension dependency to d to the 1/4 under an integration oracle. I will explain what an integration oracle is in the next section. So for practical, the takeaway is that for most practical algorithms, you can, for most practical like Bayesian models or like the problems encountered in whatever like exploration and Thompson sampling, most log concave distributions satisfy this kind of integration oracle. A nice example is again the like generalized linear model, or we call it the ridge separable functions. I will explain this in the next section. So let's continue the discussion about.
Can I ask about the previous slide?
Yeah.
So what class of functions are the last three rows for? What assumptions did you make?
Okay, so the assumption, the precise assumption we are making is that so you take a function and take its gradient, and for any line segment, you just need a straight line segment. You have explicit formula for computing the integral of its gradient along this line segment. And this is satisfied, for example, by like generalized linear model. Right? For example, if you consider Bayesian logistic regression, even with regularization term and with other some other stuff, because for Euler models, for each data point, it is usually a one-dimensional function that you really need to integrate. And you just integrate this one-dimensional function using some explicit formula or some just one-dimensional integration technique. And you combine them, sum them up to get the integration oracle for the basically empirical gradient function that you are caring about.
So you don't need convexity?
You need convexity, you need strongly convexity and smooth, but the important aspect of this class of assumption is that it doesn't need anything about the individual functions. So you need the averaged function to be, or the summation to be strongly convex and smooth, but you don't need anything about, you don't need them, their norm to be bounded, you don't need them to be incoherent, you don't need any like individual Lipschitz or whatever.
I see. So just to wrap up, so there is a dependence on kappa that's not shown here, right?
Yeah, I'm hiding. Yeah, that's a good point. I'm hiding all the dependency on kappa. There's so basically you can think of kappa as a constant, and we are just trying to improve the dimension dependency. And this is a very interesting future direction to further improve the kappa dependency. I think the kappa dependency is not necessarily due to our algorithm. I think I tend to believe it's due to our analysis. I think the kappa dependency in our paper is not tight. And we didn't work very hard to get it optimal. Yeah, that's a good point. I have to mention that. Okay, so let's continue the discussion about the difficulties with discretization. So we know that discretization of, for example, if you want to compute some integral, the discretization is something well studied, and like why is it so difficult for this high-dimensional sampling problem? Well, we know that for for example, for one-dimensional or low-dimensional discretization problems, you can, if you're just solving a one-dimensional ODE, for example, then you have a lot of methods like linear multi-step method, Runge-Kutta method, collocation method. And this method essentially is taking a few like interpolation points and try to approximate this integral using some Lagrangian polynomial or whatever. And sometimes you also need to solve the fixed point equation associated to this discretization method. And if you get k like interpolation points, you can get eta to the, roughly speaking, eta to the k discretization error, which is very, very small and which is very, very desirable. So why is it so difficult? The problem, there are a lot of things that breaks down in high dimensional problems, and discretization is one of them. The problem with discretizing this high dimensional integral is that, as we just said, the difference between the point where you evaluate the discretization point, where you try to compute the discretization, and the actual process, actual like point that this differential equation is generated, if the difference between them is of order eta times root d. Like no matter how large order discretization method you use, you get eta times root d to the power of k. And this does improve the epsilon dependency in your final mixing time. But if you want to get if you want to get better dimension dependency, it doesn't help. And actually, like no matter how many order of smoothness you have, in the end you always get like basically root d dimension dependency. And that's why actually in Santosh's work, they need this kind of it is like an L infinity version of the tensor operator norm bound, and it helps the discretization a lot. And it is a great work, but I mean it is this assumption is relatively restrictive and it's not satisfied by many models. So can we do something better? So it seems like all the difficulty lies in computing this kind of integral. So what if I give you an integration oracle? We know that for many practical problems, the form of the problem actually gives you the possibility of computing integration directly. So what if I give you a simplest form of integration oracle, which is like basically, if I give you the oracle for computing an integration of the gradient of a function along any line segment, can we use this oracle to get a better sampling algorithm? So the idea is that we know that if theta really follows this SDE, then the path for theta is actually like a curve, very like difficult to control stuff. But what if we just take a one like simple forward order step to restrict it to a straight line segment and integrate along this straight line segment using this integration oracle, and use this oracle access to further incorporate it into our sampling algorithm to like get the possibility of like improved sampling algorithm. So this gives rise to two questions. First is, under what kind of assumptions can we explicitly compute this integral? This is, of course, a question. And the second question is, even if you are able to compute this integral explicitly, but how can you incorporate it into the stochastic differential equation that you are trying to solve and actually give you a better sampling algorithm? So for the first question, the answer is relatively simple. Essentially, in order to be able to compute this type of integration, one example is you can just you can just assume the function to be of ridge separable form. You can think of it like a generalized linear model, like logistic regression. Actually, I cannot think of a practical like log concave sampling problem that appears in Bayesian inference that does not satisfy this form. And if your function actually given this form, then you are actually integrating a one-dimensional derivative, and you can just solve the integration problem using fundamental theorems calculus. And this is just a high school calculation problem and gives you this formula. And it is important to know that our result only requires the availability of such integration oracle. So if your function is written in this form, I don't care like either the individual AI has a large norm or they are like mutually coherent or whatever. I just require this function to be able to give this integration like formula integration oracle, and it has to be strongly convex and smooth. So the second question is harder, and it's a very subtle problem. If you are trying to utilize the first try, of course, we have like underdamped Langevin diffusion, and we want to utilize underdamped Langevin diffusion. But unfortunately, this doesn't work. The reason is if you want to compute the R process for the underdamped Langevin diffusion, R process is an auxiliary variable in underdamped. And it gets the two terms actually mixed together, and you cannot directly separate them. The first term is the integration oracle, which is just the integration. But the second term involves the path, the entire path. And in the middle, you still have this integration here. And like using a single integration oracle, you cannot compute this. So this, although I can write down the formula, this is not something that we can really compute using the integration oracle. So if you really want to get a faster sampling algorithm, we may want to separate the part where you integrate the gradient f and the part where you run this OU process and inject this Brownian motion. So that gives rise to the second idea, which is the high order Langevin diffusion. So underdamped Langevin diffusion is not the only like version of high order Langevin diffusion. There's like a sequence of work by Yan, which gives a complete recipe of this kind of diffusion process that gives the correct stationary distribution. So essentially, you can augment your state space into like the underdamped is augment your state space into 2D dimensional, but you can augment it into 3D dimensional, 4D dimensional. And as long as the matrix pair D and Q satisfy this assumption, it gives you the right stationary distribution. So, and the principle for designing such like diffusion process is that first we want the D to be has like less non-zero entries as possible, because like if the D process has a lot of non-zero entries, then you get injected with more noise, and this noise can make the path less smooth and harder to discretize. And second principle is that you want this Q process. Q process is like a transport part of the equation, and you want this Q process to be able to separate the part where you compute the integral of the Brownian motion and the part where you compute the integral of the gradient. And based on these two principles, we can design this diffusion process. This is a 3D dimensional like diffusion for D-dimensional sampling. So essentially, this theta depends on this P process. But P process is to compute P process, you need to compute the integral of gradient of f. But this P process does not have any Brownian motion directly injected into this process. It depends on the Brownian motion through this R process. And in such way, we separate the gradient part and the Brownian part of this process. And this gives the possibility of making use of this integration oracle and building like a sampling algorithm with better dimension dependency. And of course, if we constructed such process, the first thing we should do is to verify that this thing actually converges exponentially fast. And fortunately, this is true. And the way we do that is like recall that for underdamped Langevin diffusion, we can construct the Lyapunov function and show that Lyapunov function is exponentially decaying. And we do the same thing for the high order Langevin diffusion, and it gives you a little bit more complicated Lyapunov function. And but fortunately, we can show. As I just said, we don't really like try very hard to get the optimal dependency on the condition number. So it is possible that the Lyapunov function we are constructing is very, very suboptimal. And using a better Lyapunov function construction, we may be able to improve the condition number dependency a lot for this problem. And the construction idea, how do we get this? The construction idea comes from like very classical theory of linear dynamical system. Basically, we borrow idea from Lyapunov's stability criteria and solve this matrix inequality. So now we have a nice diffusion process with very smooth path, and the integral part and Brownian part got separated, and it remains to really discretize and get a faster sampling algorithm. So here's a informal statement of our theorem. So basically, as I just said, if your function satisfies such nice things with condition number bounded by a constant, and there exists a discretization scheme of the third order Langevin diffusion that I just described, such that if you take step size to be basically this should be epsilon to the 1/2 instead of epsilon to the minus 1/2. If you take step size to be epsilon to the 1/2 d to the minus 1/4, you get this like d to the 1/4 mixing time. And this is the iteration complexity of the algorithm, and it's natural to ask what is the per iteration complexity. And for each iteration, we invoke one integration oracle, as I explained, and some additional calculation, just like adding things together and generating d-dimensional Brownian motion and add it to the iterate, and all these things are feasible within OD time. So the per iteration cost is as cheap as computing the gradient, as long as your function satisfies some nice form. Okay, so that's how we discretize that. Oh, by the way, this discretization scheme is completely explicit, which means that you don't need to solve any fixed point equation to compute the one-step update. You just need to, I can just explicitly write down a matrix that you, based on this matrix, you can just update your iterate and get what you want. So recall that this is our third order dynamics. And the hard part lies in P. And we want to, so this P involves both the gradient, which is hard to integrate, and something that depends on the Brownian motion, but does not directly depend on the Brownian motion. So why don't we first construct some coarse approximation to the diffusion process within this small time interval for this theta process and R process. So that leads to the first stage of our discretization argument. So here, like the tilde is like P of basically theta P and R of like K eta with the tilde on its top means the last step, means the output of the last step. So our algorithm is basically an update from the tilde from tilde at time K eta to the time like K plus 1 times eta. And hat, all the things with hat are like some auxiliary process, which is beneficial conceptually for the construction of this discretization scheme, but not really used in our algorithm. So that's what we do first. We construct the two hats. The two hats are the coarse approximation for the path of the diffusion process. And of course, by the, like, again, you are integrating a d-dimensional vector, and the discretization error here is of order eta times root d for like this step and the next step for this like coarse approximation. Here's a very simple like animation for that. So you can see that basically for theta hat process, you just move along a line segment. There's no Brownian motion injected to that, and there's nothing nonlinear happening. And for this R hat, it's just run with the OU process, which is explicitly solvable as we just discussed. So we get this in hand, and how do we make use of that? That's the K step. That's the second stage of our construction, which is to to make use of this coarse approximation for theta hat and r hat to construct some approximation for the p process in this diffusion. And the way we do that, so we construct both p tilde and p hat. So actually, for these two processes, the endpoints are the same. As you can just see, the endpoint, if you just integrate the first process, you'll easily see that the endpoints are the same. And actually, algorithmically, we only use the endpoint of p of k plus 1 tilde. And this thing is computable through an integration oracle. So what do we do is that we conditionally on all the information up to time k eta. You first invoke the integration oracle and compute the integral along a deterministic line segment. Know that this line segment has to be deterministic. We cannot support any like integration oracle on a stochastic path. And then, given this, we use this to compute this OU process. Everything else is a joint OU process. We make use of this and compute a joint OU process. And so this p tilde of k plus 1 eta is directly integrable using the information given to us. And the important thing is that although the amount of move within this eta time is still offered eta times root d, but if you try to align this p hat process and p tilde process, their difference is over the eta squared times root d. And that's why, like from very, very high level reasoning, that's why like it is possible to get like d to the 1/4 discretization error. So here's what we are actually doing in this step. So this is just a conceptual construction. This is not the way we really run the algorithm. The way we really run the algorithm is that we like compute all the explicit constants and just do some matrix multiplication, 3 by 3 matrix multiplication. So suppose we are given the path for theta hat and r hat, which is a line segment and the OU process, and this p tilde and p hat are just constructed by tracing the path, tracing the both paths, and integrating. And in the end, they should end at the same endpoint because the integral involved in p hat is just an average version of the integral involved in p tilde. And here's the last stage of our construction. So basically, this part gives you the final approximation for theta tilde and r tilde in the last step. And the way we do that is we make use of the p hat process. We know that p tilde is something we have conceptually in mind. P hat is what we really use in the construction. And but they are not too different, as I just said. Their difference are bounded of order eta squared times root d. And by integrating this p hat process, you get a like final approximation for the path of theta and final approximation for r. And this thing is the initial point that you use in the construction of the next iterate. And it is important to note that if you try to align the tildes and hats at the same time point, their difference is always of order eta squared times root d instead of eta times root d. And this gives the final like eta times square root d final discretization error bound. So the way we do the last step is, as you can see, so basically we track the, so p tilde and p hat track the move of theta hat and r hat. And further, like theta tilde and r tilde track the move of p hat. And everything is explicitly solvable using the integration oracle and joint like 5D dimensional OU process, which can be explicitly computed. And this gives the final result. So here's the main takeaways. As I just said, we basically make use of this special structure that allows for this integration oracle, and use high-order Langevin diffusion to get a faster, like high-dimensional sampling algorithm with d to the 1/4 mixing time. It is relatively easy to implement. It's a bit hard for algorithm designers because we really do a lot of manual calculation to compute all the constant in the update equation, but it's very easy to implement. And there are a lot of open questions if we want to pursue further research on this line. First, it is natural to ask, like third order Langevin diffusion give you like d to the 1/4. If we do like fourth order, fifth order, can we do something even better? And my conjecture is that it requires integration oracle along a like polynomial curve instead of line segment. So you can think of like some higher order polynomial, and it will further improve the dimension dependency for sampling algorithm. And actually, EI is going to present a work which partially solves this problem, but using a different approach. And they are based on strictly stronger assumptions. So it's does not directly solve this open problem. So this problem is still open. And the integration oracle is not something specific for sampling. I suspect it could be also used for certain scenarios in optimization or discretizing like ODE or PDEs. And also, like, it is still not sure if you don't have this integration oracle, is there something that you can do to actually improve the dimension dependency using only the gradient oracle? Okay, that's all for my talk. Thank you. Yes.
So there have been other third order algorithms presented in the past, for example, thermostats and so on.
Yeah.
Is there any connection, or those improvements somehow can be explained with your theory?
I think the motivation for the construction are like somewhat orthogonal, because we use this for particular reason of high dimensional discretization and to make the path that you want to integrate much smoother. But it would be interesting to see if our analysis technique or something can have some connection to them. Yeah, has a question. Okay.
What we found in practice is that for thermostat kind of method, it is also third order. The benefit is that it controls stochastic gradient when you have a stochastic gradient query. So it's really orthogonal to our work.
More questions?
Yes. This one?
So I guess I'm just confused. Like, what in what sense is this an oracle? Like, what is the actual computational step that this is substituting for?
So it's like if your function is really given by this form, then I just give you this formula to compute the integration. This is exact.
I see.
Yeah. I mean, there could be other functions where the numerical integration along a line segment happens to be easy. And our analysis also applies to such problems.
Thank you.
Let's thank Wenlong again. And, we'll start at 2:50.